I have some nice things to show you. Here's money. German marks. And this is the money which will disappear next year. So, you know, the European Union agreed to disappear with their own money, and they introduced the euro. And in the euro, they have the problem whom to put on the coins and on the money. So they agreed if they have a common currency, no heads anymore. So that's the last time you can enjoy Carl Friedrich Gauss on a 10-mark bill, a German 10-mark bill. So that's the reason why I'm carrying that always with me. But it's only valid for the next maybe 1.5 years, and then it's gone. So everybody who goes to Germany, I hope you have seen it and know about it. And here you see in the back, you see the normal curve, what we will do today, the normal model. And I made here, actually this is not allowed, I guess, to copy money, but for scientific purposes, as we do it here now, it's possible, so you get it larger and larger here. It's this way around. And some people claim they made a little bit of a mistake here, because they give here the formula. Actually, they have the formula of the normal curve. So if you're sitting in a German class and want to make your exams and forgot, just a moment, the normal, here it is. So people claim it's the normal 0-1 curve, but if you look at the scale, it's actually the normal 3-1 curve, because to be on the positive side, they shifted the mean to the number 3 here, and that's what you can see. So I made it even larger now here. See, this is the story about Gauss, but I guess we cannot make any Gauss lecture here, so now you see it really nicely coming up here. And by the way, I think that now the new the coins can be different. So they agreed with the euro coins that one side can be different from nation to nation, but the bills have to be the same. And to show that everybody belongs together, only bridges are shown on this new money bills. So this is so much for the history now on what we can see on statistics on bills. Here I found out we have MG on the 100 rupee bills, is it? I haven't examined the other ones. And actually in Switzerland we have now new money where some parts are written in very tiny letters. And they had a bet on the TV going on, so somebody can read what is written on this bill, which nobody can read except if you make a magnifying glass or have and so on. Okay, so much for the lunch break, and now back to work. So I was asked to do it rather smoothly, and now we go more in details of the technicalities of all this linear models in time series analysis, and I will ask you to follow that. So we will have about 1 hour for the first part, and then some more on structural breaks and outliers in the second part. And I will check then if the computer system works on the last lecture and try to make the bridge to the application. So now we are back to the Bayesian linear regression model. So we have two ways of writing it, either as an equation here, xt prime times beta plus epsilon t, and then xt is this vector of regressors. We have capital K regressors here, and we have n observations. We will change that if it's a time series or a cross-section from n or capital T observations. And then we have this regression vector beta, beta 1 to beta k. And if you write this in a normal distribution, if you assume normality for the dependent variable, then the mean is x beta, written x here as a matrix, n times k matrix, and the beta is the same vectors here. And of course, in the beginning, we assume that homoscedasticity, as we call it, one variance for this identity matrix of order n. And we will later on will make this assumption more general, so we let so-called heteroscedastic models or arch models be present in these regression models. So this is sigma square is a scalar, and the total parameters we have to estimate is k plus 1, the beta, and the sigma square. So this is number 1. Well, just simply to say that a different way of writing it is in this additive form. So where epsilon is the error distribution with 0 and the same variance matrix, and for this design matrix, we make this assumption that it comes in this form. So the theorem, which is the extension of the simple model, which I've shown you just in the first lecture, is now the so-called normal gamma regression model. And I write it in this box. So this comes more or less in 3 steps. We have a prior distribution. Prior, it's called for reasons which comes from philosophy. Prior means before you have made any empirical research, what you think, what is in your head about the parameters. It's not always as ideal as we think it is, but here is the prior distribution, and now we extend that to the so-called normal gamma model for a vector. So a normal can have here a dimension k, so you know it's a k-dimensional normal distribution, and the extension is quite visible to see. It's now beta star is a vector and h star is now a whole matrix, while the rest stays the same as we had it as star squared and n star. And we have a likelihood function, what we think is how the observations are generated. In this case, it's the normal distribution by which was due to Gauss, but also Laplace, I want to say, has derived his own way of normal distribution, but probably somebody else has to report on that for another Laplace lecture on that. And this is normal here, normal in the prior. And what you get out as a theorem, and you can show that, but we will not do that here, but the good textbooks like Arnold was one of the first ones who showed it, and other people, now a recent one is by Poirier, I guess, they give the proof. So out comes that the posterior distribution of beta and the precision sigma squared is the normal gamma distribution, B double star, H double star, S double star, N double star, so about the same form as above. Therefore, it's a conjugate model. We call this again conjugate model. But of course, now their way how these parameters are computed are different. Again, remember, 1 star is always an indicator of a hyperparameter of a distribution. In this case, it's a normal and a gamma distribution, as is indicated here with the name. And the double star is always a parameter of a posterior distribution. So we have these 4 parameters. So this is a notation which originally was suggested by Lima, but I think Morgenstern and Reifer and Schleifer, they had it with prime and double prime. So this idea of having some kind of very obvious notation is rather present in many of the books. So this is why is a normal gamma distribution? People will ask why you can't write it as a normal and a gamma distribution. It's not possible because the normal is a conditional normal, the conditional under sigma, while the gamma is a chi-square essentially distribution which is independent. And to show you this, that's a normal gamma distribution in 2 dimensions as we had it for the simple model today. but it's similar in higher dimension. So this is how it would look like if you draw it as this grid. And here is it if you have this iso density curves. And here in this direction it's always the mean, and that's where the precision is done. So if you cut here in parallel lines, so horizontally, this always will give you a normal distribution. And if you cut it horizontally, it will always give you a gamma or a chi-square distribution. So that's the interesting thing. And inference, Bayesian inference, is now learning from the data by transforming this normal gamma distribution from a priori parameters to posteriori parameters. So not knowing too much means you have very wide isodensity curves, and being informative means you're on the same scale, as I try to be here, on the same scale, rather peaked. So that's the idea. So lots of learning goes on if you have a situation like this, where you go from a relative flat joint distribution to a relative peaked one. And if you look at this, you see the peakness here comes up as almost like a slice. And in many cases in economics, we have this type of situation that you're very informative in certain direction, but less informative in other directions. So this is a rather common situation, what you see here. And interesting, as you told you, every time you have a normal gamma distribution, and you try to make an average over all these normal curves, which are sitting here in parallels, then you get, as an average, a t distribution. So this is a mathematical fact. If I would have time enough, I would show it to you. So now how are these parameters are now calculated? And again, this is on the first, probably, are any people familiar with the normal gamma Bayesian model? Hands up. So some people, yeah, you know. So here I give you a little bit of insight. It's quick, and you need some days usually to digest it, what is going on here. But it's just to have seen how this works. That's the way how it is done. Let's always start with the easy part. The easy part is here. I hope I'm not too much up here. This is here the precision. So we had, remember, we had in the univariate case the precision, the posterior precision adding up from the prior precision plus the data precision. And the same thing here. The posterior precision is now a precision matrix. We always call the inverse of a variance matrix the precision matrix. So we have here the prior precision matrix plus x prime x is the data precision. So this stays the same. Then for the posterior mean, we have almost the same formula, but now in multivariate case, it's an average between the prior mean, and you can't see it here, but this is the average. If you write it a little bit differently, x prime y can be written as x prime x b, or beta hat, b I call it here, where b is the OLS estimate. So this is the same value. If you plug it in, you see that. And this tells you that we have two location parameters, the prior mean and the maximum likelihood location, and OLS in the same case, which are weighted by two matrices, the x prime x matrix and the inverse of the prior variance matrix. So you should see at the same moment, if you're very flat prior, then the variance is big and the precision is small, so this cancels out, and then you're back in the so-called diffuse or non-informative case, where you just have here the OLS estimate. So that's the philosophy. The data tells you, or the relative weight of the OLS estimate compared to the prior mean. If you don't trust the data, then the prior will have more weight. If you don't trust the prior, then the data will have more weight. So the next thing is the stuff with the variance. So we have the degrees of freedoms for the variance, which is denoted by n double star. It's the prior degrees of freedom plus the number of observations. And again, we have the posterior degrees of freedom multiplied by the posterior variance. This we call posterior error sum of squares. So the posterior error sum of squares is the prior error sum of squares plus the data error sum of squares and the discrepancy vector. And this discrepancy factor actually is here a number, and is calculated from the difference of the vector, the difference of the location parameters up here, the b star and the b, in this metric x prime x and h star, which is just the inverse of this in a certain extent. So usually this is small, but in case they are far away, you get penalized as well, and you lose in precision. So having bad guesses about where the data are, and you have not matching views, then this tells you be careful in your inference, rather be a little bit larger than just in the classical case where they would operate with this ns squared here. The ns squared is shown here. It's just the error sum of squares. So this is the residual vector of the OLS regression, and this is the residual vector, and this is just the residual sum of squares, and b is just the OLS estimate. So this is essentially the formula for the multivariate case, and we will have one more step for multivariate regression, the same with what Bill Griffiths did for the seemingly unrelated. We'll need it for the multivariate time series framework. Just one more remark. This discrepancy vector here can be calculated in a second way, and this is denoted here. So this difference here between b star and b can be written in this by these three quadratic forms. So the y prime y and this prior and this posterior quadratic form. Okay, that's the way now how we can calculate the posterior parameters. And remember, we are still in the normal gamma framework, but now in the matrix version, vector version. And this is are the four parameters, and we show you how to calculate it. And essentially, it follows from Bayes' theorem, where you plug in all these ideas. I haven't now done this explicitly, but it's always prior distribution multiplied by the normal likelihood function, and then you do the appropriate transformations, which is essentially mathematics, combining quadratic forms and identifying the right distributions. So one more step here in this analysis. So we have now a k plus one dimensional distribution. I've just showed you a picture how it will look like in 2 dimensions. So if you want to make inference in the lower space, then the idea in Bayesian statistics is marginalize. And marginalize means integrate out the parameters you are not interested. So if you're only interested in beta, given the data, y, then you have to integrate out the precision. And every time I told you, and that's also extending to this multivariate case, every time you have a normal gamma distribution and you integrate out the variance parameter, you will end up with a t distribution. That's exactly what is going on here. So again, the proof is in the book by Arnold or other Bayesian books. We will get here posterior distribution for beta alone, which is now a k-dimensional t distribution, and it follows more or less the rules for the simple case, the one-dimensional case I showed you this morning. So we have the location beta double star for the t distribution. We have a scaling matrix S double star times H star, and we have the degrees of freedoms, which are completely determined by the degrees of freedom of the variance distribution, of the precision of the gamma distribution. So I think it's important to notice that now we multiply this H double star with the posterior variance S star, which you have to calculate by this rather more complicated formula. if you want to describe this by moments, here again, this is my notation for moments in this type of brackets. It's the mean, which is invariant, be the double star, but the variance matrix here is different from a t-distribution. You have to inflate, make a little bit larger, the scale matrix of the t-distribution by multiplying n star divided by n star minus 2. That's the only difference. And you see asymptotically this vanishes if you have large number of observations. This ratio is 1, and the scale matrix is indeed the variance matrix. Again, if this can be a very big vector, for instance in the time series case, we want to make inferences for single coefficients. What you do, you just take the marginal distribution of this multiple k-dimensional t-distribution, and essentially there are the diagonal elements of this k-dimensional t-distribution. So if you're interested in only one particular coefficient, then you take out this particular posterior coefficient beta I star and the particular diagonal element of their scaling matrix, and the degrees of freedom stay the same. As I told you, this posterior mean can be written in this matrix weighted average, and Lima, in his book 1978, has a theory about how matrix weighted averages can be described if you don't specify, for instance, completely this prior covariance matrix. Then you get something like posterior robustness. That's a Bayesian robustness concept, but people have not followed up this idea. They like precise answers. Again, the Bayesian model specializes for the so-called non-informative case to the usual or classical inference model for the regressions. And this special case follows if you assume here this Jeffrey prior for the beta and precision sigma inverse squared, and the likelihood function is the same. So you can really follow that as a rule. Some people say it's like a mill. So if you put on at the top the prior and the data, you know what, you turn the crank, you know what is coming out. It's the posterior distribution, and the posterior distribution in this way of writing is now a normal gamma distribution with their mean B, the OLS location, B OLS, and their actually this is 1 sigma s squared too much. Here it's x prime x inverse for the matrix of the normal distribution, and s squared is the scaling scaling factor for the gamma distribution for the precision, and we have n minus k degrees of freedom here. And if you want to make a conditional inference, then you get the normal distribution, but conditional on the knowledge of the variance. So that's the way we will get out the posterior distribution for in the non-informative case. Is it the same as the classic case? Yes and no. Why it's yes and no? Essentially, it's a different. The numerics is more or less the same. So you get the location parameter B, and you get the t-distribution as we know it from classical distribution. But the basic difference is now that beta is still a random variable. So always we have always random variables in Bayesian statistics, and everything else is conditioned on their sample. So all of those parameters you see in here as a t-distribution, as parameter of t-distribution, or as a parameter of the beta of the normal gamma distribution, is a constant, and not as in classical case as sampling distribution. That's the big difference. So numerically it's more or less the same, but the interpretation is completely different. And again, if you want to, for the non-informative case, to describe this regression vector as in terms of first and second moments, then you have nu over nu minus 2 times s squared x prime x inverse, where nu is the degrees of freedom n minus k. And s squared in this case is the sampling variance. So that's the idea of the Bayesian regression model. And if you could follow this, this gives you a very powerful tool and insight what can be done by this linear model. This linear model, as it has been done previously, and apply certain prior structures. So what was very popular in the 80s, so almost last 20 years now, was the so-called Litterman or Minnesota prior, which assumes a tightness structure, as they call it, on the coefficients. So if you use this linear model to estimate an autoregressive process, I warn you a little bit that some people don't think that's the right way of doing it, and you can derive the likelihood function for an autoregressive process a little bit different. But in econometrics, we like to think in linear models, so we always try to fit everything in this linear regression framework to estimate the regression, the time series models as well. So how we will do that? So what we'll do is if you have an autoregressive model, which I haven't written down here now, which I see, so I have to write down what is an autoregressive model. In this case, it's yt equals beta 0 plus beta 1 yt minus 1 plus and so on, beta p yt minus p plus call it, I think, ut or epsilon t, the error term. So we think that the current observation is generated by p past observations, yt minus 1 to yt minus p, and beta 0 to beta p. P are the coefficients. If you have this ARP model, and we assume normality for the error terms, then we are back in the normal regression model. So we can assume for the vector b, beta, and the precision sigma inverse squared, a normal gamma distribution. Again, in the same way, beta star, h stars, s star, and n star, having the same meaning that conditional on sigma squared is a normal distribution, and the marginal for the precision is a gamma distribution or an inverse chi-square distribution, or a chi-square distribution for sigma for the precision. And assuming a prior structure here means the following. We think if the data are stationary, that the prior beta star is 0. So it's as a process which is appropriate for first differences of economic time series. So we think that if you have growth rates, then it's on average we can't say if the coefficients are positive or not. They will center around the 0 line, but the only thing what we can say is about the precision matrix H star inverse, or the variance matrix, that we are pretty sure that the further we go back in time, the smaller will be the variance. So we are pretty sure that the coefficients in past legs, like those in the back, will be rather closer to 0 than in the previous legs. And this is expressed by this tightness structure. And Litterman was one of the first people who applied this. He came from the Sims school. So Sims had written in the early 80s, 1980s, the famous article about macroeconomics and reality, where he introduced vector autoregressive models for forecasting and for simulations of dynamic models. And they were the first one who introduced this type of priors. Therefore, it's also called, because it was developed in Minnesota, the Minnesota prior. And the tightness structure essentially says that for the intercept, we are rather non-informative. That is, we cannot put it at 0 here, then we get problems. But yeah, so actually, what you could calculate in a Bayesian framework is because you condition on the data, and you can have a prior which is essentially extending over the interval -1 +1. The probability that a process is exploding on the positive side or the negative sides, and that some people did, like I think Schultman van Dijk, they calculated under certain prior conditions these probabilities, and they also did some sensitivity analysis, because we know that it depends now then on the prior, or what the posterior probability is that the process is non-stationary. So you can do a little bit of sensitivity analysis. That's one of the idea. So but coming back to the to this prior distribution, so tightness structure means that we think it's 0, and if you think it's a non-stationary process, that was the original idea by Sims, then you think the current value is influenced by the past value, and then by a lot of other lags which are 0. So the past value has then the prior 1, and the other coefficients have 0. But if you're modeling it just in first differences, as we will do it here, the difference in the logs of here, then this tightness priors essentially says, I don't have the right picture now here available. There you start with a flat prior for the intercept, because we don't know where this intercept will end up. But the farther we go back here in time, the more we are sure that the coefficients will be close to 0, and because we don't think that very long lags will influence the current very strongly. It's rather the case that the recent past is much more of influence. So this is tightness, and this is expressed by this prior structure here. And then we have to assume another prior for the residual variance. As I said, the epsilon here is taken to be large. This is for the intercept. And for sigma squared, we think usually that we can explain about 90% of the residual of the variance of the model by an autoregressive process, and this prior information has a value of 1 observation. That's essentially the interpretation of n star equals 1. Again, then, if you assume this model at this prior, then you fill in the X matrix by this past coefficients. So the X matrix is essentially a vector of 1, then the 1 lag back and 2 lag backs, and so on, until P lags back. You construct this matrix, and then you're in this linear framework. And we can apply the model, which I just showed you, that we have a normal gamma distribution, and this is the result as we had it before. Maybe I just tell you what the mean and variance of the gamma distribution is. So there, for the sigma squared, this is S double star minus 2, and the variance is 2 times n star S double star minus 4. So it's 1 square more on the variance of the residual variance. And here the posterior moments are given, as we discussed it before, as as a mated average between the prior mean and the maximum likelihood location. If the prior is 0, then essentially what you're having is that this term is not important, but only this part here. And what you see here is you get some kind of rich estimator, as it was called in classical analysis about 30 years ago, because x prime x is built up by this time series, and the time series are highly correlated. So what you end up usually is with a highly collinear or almost collinear matrix x prime x, which makes difficulties in working in high dimensions. But if you add here this type of diagonal structure, this makes it much more easier to work. And what the effect is numerically, you get much more stable estimates of the coefficients. And that's probably also the case if you do then the forecasting. And this model was tried in forecast very successfully. And there was a famous article about a forecasting competition by Makridakis, I think in the 80s. And the Bayesian model always won. And Arnold, I remember you had an article written that the Bayesian night strikes again, and you pointed out that the best models in this forecasting.
It was another Bayesian.
It was about a similar Bayesian model with a similar idea that putting a little bit of prior structure on such coefficients which are very erratic in a behaving in a classical estimation procedure becomes very sensible if you just add a little bit of sensible prior structure. So that's just to tell you why this is good, and people have used it extensively then in econometrics. Again, if you do prediction, then we have to calculate the predictive densities. You can calculate the predictive density just for one step ahead, which is yt plus 1, or you can do it for more than one step, and the formula is a little bit more complicated. But essentially what you get is a t-distribution with x prime t plus 1 and beta double star. So you have to specify a future vector of x, which is probably evaluated usually at the posterior mean. If you put in here the xt's, I don't go now in details how to do that, and then you have the predictive variance matrix here, which is S double star and M double star, and M double star is essentially the matrix which you know from. It could be in general a matrix, but here it will be a scalar as well. But this is the same type of matrix you have seen probably from classical statistics, where you have a 1 plus the usual linear combination formula of variance. But the variance here is now the posterior variance H double star. And the predictive distribution is conditional on sigma always a normal. But if the number of observations is large enough, then you don't have to use the t-distribution. The normal distribution will be okay, because these degrees of freedom will be close to 1. So that's the theory, how to do simple autoregressive models. And what is left open now is, what I haven't told you, how to select the right models. What is the way of order selection? And the literature was full about in the last 20, 30 years how to select it. There was the Bayesian or the archaic information criteria. So how we should select now the model from a Bayesian point of view. And this is now, I will not go too much before the break into details, but this is now the outline of the next hour. What we will do, we do structural breaks and autoregressive model links, and we will tell you now what the marginal likelihood is. This is a simple extension of this normal gamma model, which I just showed you, and it is part of this Basel package, and the paper also appeared about 2 or 3 years ago. and we discussed it. And what I like about the paper is that it's the simple structure, and it has quite what we found out good empirical applications. So, for instance, we are interested in modeling those two time series for an economy, like here for Switzerland. This is GMB and consumption in Switzerland, in real terms, quarterly. And that's their old consumption model, and people want to find out, for instance, are those time series stationary? Are they hit by some structural breaks? And are they now co-integrated? If they are integrated, these models, how to test for them, as we just talked about unit roots, and are those two time series connected or not? What means connected for random walks? That if you look at the difference between the two processes, are the differences of the two processes stationary or are they non-stationary as well? If they are stationary, the differences, then we call them co-integrated. And that was the concept which was developed by Engler and Granger in the last 15 years. And another famous analysis out of this macroeconomic data is the consumption function. Workers and they claim that created a large drop in GMP and consumption, and then finally it caught on in the 80s. We see that consumption was developing more smoothly than GMP. GMP shot up until 92, about in the early 90s, when the Swiss had to vote to join the European Union or not. That's what brings us back to our coins and bills at the beginning, where now the Swiss will have the Swiss francs, but the rest of Europe will have the common currency, and the Swiss decided not to join. And you see what happened then, the GMP, it flattened immediately. So the expectation economics were not too good. And so after the 7 meager years, I will say now in the 99 and 2000, now we are hoping that the Swiss economy catches up again. And so this is the type of analysis we are going to analyze. I think now after the a short break for the movie after 20 minutes, so you can prepare to get some relief with time. Now it becomes a little bit more complicated, I guess. But it's unfortunately late in the evening. I will not stress too much because Arnold is giving another talk. I hope you're all coming to this economic talk, real economic talk. We are just talking about methods, but then the real implication for the future of India, that's what we'll hear this afternoon. Why not? So you see, I'm still here thanks to all the efforts. We called Delhi and Bombay and Bangalore office. They still haven't kicked me out here from so I still can be with you, I guess, until the end of the week. And I'm glad it worked out so nicely. It was according to misinformation that all this stuff was working against a smooth start. But now back to Bayesian testing in autoregressive processes. So I give you some summary of test statistics or test procedure, which is best summarized in the word marginal likelihood. Marginal likelihood is some kind of miracle work, a word which emerged in the last 5 years, also in connection with the Gibbs sampler, which I haven't shown you today, but this will be a natural extension of all these autoregressive models. So what is Bayes' theorem? Now we are back to the basics. Bayes' theorem says that the posterior distribution is a product of the prior times the likelihood, we have seen that one, divided by a constant, which is called Fy here. And this constant was neglected for a long time, but it has tremendous implication. It's the marginal likelihood of the model and can be used for testing, for Bayes. So now we developed in the last 5 years several techniques how to recover these constants, which was really suppressed for a long time for various reasons. And now we find out that it's important. So that's the decomposition. The joint density can be written as a likelihood times prior, or the posterior times the marginal likelihood. That's just the integration constant in all times. And why is this important? The marginal likelihood is the ingredient for the Bayes factor. So the Bayes factor can be expressed in the following way from the joint distribution between two models. So we have a model 1 and a model 2, which gives rise to two joint distribution, f theta 1y and f theta 2y. And if you integrate out from these two distributions, the parameter vector theta 1 and theta 2, which can be of different dimensionality, then we get the ratio of two marginal likelihoods. And the ratio of two marginal likelihoods is the Bayes factor. So the Bayes factor summarizes all the data evidence. It doesn't depend anymore on parameters because all the parameters are integrated out. And gives you, now the Bayes factor gives you a weight, empirical weight, some measure of evidence. Is the model 1 better or the model 2 better? If they're equally good, then the Bayes factor is 1. If 1 dominates 2, then the Bayes factor is larger than 1. So you should go for the larger, always go for a model with a larger marginal likelihood. And if the F2 is supported by the data better than F1, then the Bayes factor will be smaller than 1. So you should use the second model. And I came up with what I call something like the 1999 rule. So all the Bayes factor between 1 and 9, they are supporting, but it's nothing really too dramatic going on. All Bayes factors which are larger than 19, the number 19, either above or the reverse Bayes factor would give you the evidence in the other direction, is significant in terms when we use the classical word significant for Bayesian classification of evidence. Between 9 and 19, the models are better supported, almost significant, you can call that. So everything above 19 up to 99 is in the range of 5 and 1%, what is used as evaluation of significance in the classical framework. And everything above 99 is highly significant. So that there is a simple rule if you look at Bayes factors, easy to remember how to qualify this. And you also can go by the log Bayes factor. And the log Bayes factor, this is roughly something like 2 to 3 to 4. So this, if sometimes the log Bayes factor, because the log marginal likelihoods are easier to calculate, you can get a rough guess what is going on between two models if you stick to this rule of thumb. So, yeah, coming back. So, sorry, I'm not done now. So the Bayes test formally is now the following. The Bayes test transforms prior odds to posterior odds. In the same way as we did for the inference, that we transform prior knowledge to posterior knowledge by transforming appropriately with the data, the prior distribution, we do the same for testing. Prior odds are transformed via data evidence to posterior odds, which is called with a double capital W, and the small w are the prior odds. And the Bayes factor is the only source where the data information comes in. And the data information comes in by these two types of marginal likelihoods. F1 and F2 are marginal likelihoods. And all what I will tell you now is how to calculate these marginal likelihoods. So, going back to our linear model. We know that now. Here's the autoregressive model I've written down here. We assume a normal prior, a normal likelihood, normal gamma prior. Actually, the normal has not to be a normal in the general Bayesian setup, But to make the things easy, whatever easy now means, and calculable in closed form, normal distribution is incredible help. But we can calculate for t and other distributions, but then you have to use MCMC and other methods. We know the marginal likelihood, now not concentrating anymore on the inference, not on the estimation of the parameters, but now for testing, then we would be only interested in the marginal likelihood of this model. And the marginal likelihood is given by this type of expression. And now I have to explain you this type of expression. You're only familiar with the H star is and double H star, so you know that all are here parameters of either the prior or the posterior distribution. And what the marginal likelihood comes out in all of these linear models is essentially three type of factors. It's a ratio of determinants, it's a ratio of gamma distributions, and it's a ratio of error sum of squares. The prior error sum of squares divided by the posterior error sum of squares. Here you see that the degrees of freedom are n star for the prior and double star for the posterior. And again, you see here the gamma n2 star is more or less n t factorial. So if n star is the smallest possible degrees of freedom, which is 1/2, then gamma of 1/2 is square root of pi. So you know this is a constant, and here is essentially the factorial here. And here you have the ratio of determinants. So what you can say is that the marginal likelihood is dominated by these three types of components, where you have a little bit of a pi sitting in front here. Sometimes you can put the pi in the error sum of squares because it will cancel out by some mathematics, which is easy to see. So the marginal likelihood is the higher, the more observation you get, because then the n double star, which is the number of observations dominating here, will go up. It's higher if the posterior sum of squares is smaller, because this is more or less a constant, the prior sum of squares. So the better the fit is, the smaller will be the posterior sum of squares. It will shoot up. And what you see here is it depends on the ratio of these matrices, the determinants of these matrices. If the determinant, the posterior determinant is larger, then also the marginal likelihood will be larger. So that's the formula. And these have to be calculated. Now, what happens for the marginal likelihood in the non-informative case, in the diffuse case? Diffuse is also non-informative. So in this case, the marginal likelihood reduces to three factors essentially. The posterior determinant is now x prime x. Then the error sum of squares sits in directly without any prior sum of squares. And the gamma function is t minus k half, and then you have here half constant also here. So the formula is extremely simple for this non-informative case. The only problem is you cannot use it because for non-informative cases their base test is not defined. You can find out because the base test is usually always a ratio of ordinates, of prior ordinates and posterior ordinates, and if the prior is a flat prior, then the concept of a prior ordinate is not defined. But we use this formula in the following idea, which is the so-called fractional marginal likelihood. which was suggested by O'Hagan by using so-called fractional base factors. So the idea is if you want to be non-informative, as close as possible, but not using this formula, we use the concept of fractional prior distribution, where we use a fraction of the likelihood as a prior. And this fraction parameter is a b. It's called here a small b. Unfortunately, it will interfere with our notation of the coefficients, but I think it's a scalar here, and it's quite clear. It's a fraction between in the interval of 0 and 1. And if we employ, in a minute I explain more about this concept, if we use this concept of a fractional prior, then something nice happens. This ratio of determinants is not anymore present, it cancels out. So we get, instead of the determinants ratio, we get here the b to the t minus b minus k half. So this is the factor which is now in here. We get the data sum of squares times the pi multiplied and this exponent. And then we get again a ratio of gamma distributions where it's essentially the gamma of the degrees of freedom. And here we normalize more or less by this factor tb minus k. Then you can ask, what is the smallest fraction number which is supported by this formula? And then you find out it's k over t. If you insert here, then exactly this t minus b minus k half becomes 0, and gamma of 0 is 1. So this is the minimum, some kind of minimum fractional prior you can use here. And the formula extremely simplifies for this case. Then this first factor is not anymore present because b0 is 1, and you have only the error sum of squares times to the exponent t minus k times this gamma distribution, and that's essentially the fractional marginal likelihood. And the nice thing about this, you don't have to worry about the prior distribution. Some people say it's an advantage, especially for a beginner in Bayesian statistics, and is to find out how much difference we have in the model choice if you employ, for instance, a tightness structure prior and this type of fractional prior. And that's what we did in this paper. So again, let me explain what is a fractional base factor. Okay, we stop here.